Hello, my name is Jacob Wood, and the purpose of this video is to test the infrared sensing block within the Smart Luggage Design project. This block will be used as a form of edge detection for the block, or for the system later on. So here you can see the block diagram, some corresponding interfaces, and the properties listed. I will be referencing this block description document throughout the testing of the interfaces. And then further down, how I will be testing the interfaces and some of the validation for said interface. To test the power supply interface to the IR sensing block, I will connect the IR sensing block to a testing Raspberry Pi and run a measurement capturing function and use this power supply, set it to the maximum 5.2 volt output. You can see that the IR sensor is measuring distances there. We'll start the testing program to see that we are indeed getting measurements back to the microcontroller. And then we will measure the current running from the power supply directly to the block. The block consists of the analog sensor itself and an ADC chip. So both of these are pulling about 26 milliamps nominal. The ADC module sends a 10-bit serial value back to the Raspberry Pi corresponding to the read in analog voltage from the IR sensor itself. So we'll power this with, again, the 5.2 maximum voltage, and we're going to probe the output line from the ADC. We could also read in the value from our testing script, and it would be 0 to 1023 before conversion. So I'll take a screenshot of this output on the oscope. Here we can see the captured output data to the microcontroller. If we zoom in, we can actually see the vertical lines of where the clock pulses would have been to clock out another bit. And so there are actually 10 bits being clocked out, but one of the bits is held longer because it's sent in 8-bit segments. So we will actually see 11 clock cycles in total. And you can actually count the pulses as well in between the individual bits, and you can see there are 10 visible sharp pulses corresponding in 10 bits being clocked out. To test the available output channels on the ADC itself back to the Raspberry Pi microcontroller, I'm simply going to run the testing script on one of the output channels. You can see it's running there. And after several measurements, you can see it's changing as I move my hand back and forth at the 5.2 input voltage. You can see the serial value changing as well. And I will actually change the input channel. It's currently at channel 0. I'll swap it into channel 1 here. And if we go back to our testing program, we can see that we are now reading values in at the different second channel. And we can also see this on the oscope. To verify that the block is communicating via SPI protocol, I will run a testing script on the IR sensor block itself and supply the 5.2 maximum input voltage and probe the master in, slave out, and master out, slave in channels between the microcontroller itself, which is a Raspberry Pi, and IR sensing block. So here we can see the master out bus on the blue line and the master in bus on the yellow line. If we analyze the expected input and output into the ADC's SPI buses, we should see a start bit coming in to the ADC on the master out bus, followed by about 6 clock cycles and the data being clocked out serially out of the ADC. Now if we compare this to the actual captured output from the ADC, we can see the data in bus in the blue up there, and we can see the first start bit followed by a control bit that is unimportant, and about 6 clock cycles later we can actually see the driven low signal on the output data from the ADC, which starts the output data from the ADC to the microcontroller on the master and slave out bus. And this serial data is it is a 10-bit value. To test the minimum measured distance of the IR sensor of about 10 centimeters, I have suspended the sensor, measured out about 15 to 10 centimeters, supplied the 5.2 maximum voltage. You can see this on the O-scope at the output of the analog sensor, and I'll use a reflective piece of paper at about 10 centimeters and read in the data on the Raspberry Pi, do a simple calculation to get the voltage this corresponds to. So we can see we're getting about 2.3 volts back after conversion to the Raspberry Pi pretty consistently. And if we check the data sheet of the analog sensor, we can see that at 10 centimeters we should be at around 2.3 volts. To test the maximum measured distance of about 50 centimeters, we will do a similar test to the 10 centimeter test. Resulting in the same plot, we can see that at 50 centimeters we should be around 0.6 volts after conversion from the ADC to the Raspberry Pi. So I'll set the output or the input to the block at 5.2 volts max, set the reflective paper at 50 centimeters, which is about 19.6 inches, and we will look at what the testing script is returning. You can see that we are consistently at about 0.6 volts here. To test the maximum measurable incidence angle to an object or ground, I've set the sensor up about 15 centimeters from the surface and at a 60-degree angle from the vertical axis. So using a little geometry, we can deduce that this will be about a 30-degree angle to ground, provided 5.2 volts maximum input, and we'll try to focus in on the output of our testing script, and we can see that we are at about 0.8 volts consistently. If we compare this to the IR sensor's datasheet, this would correspond to about 30-35 centimeters, which is about where we would expect the hypotenuse of our 30-60-90 triangle to be about if the height is around 15 centimeters.